Well, just to finish my thought about the second blue whales problem, again, this sample size was much higher. And I think something I forgot to mention was that the probability is terribly remote. As you can see, 0.0062. So the probability that the sample of 25 whales will have a mean weight of 200,000 or lower is off the charts low. I mean, really, really low. And again, someone might say, well, geez, 200,000 looks like it's in the neighborhood of 220,000. But again, bear in mind, you're talking about means of 25 whales, not individual whales. And that makes all the difference in the world. And as you can see, that's a terribly low chance that mean of a sample would be lower than 220,000, less than 1%. Let's talk about just another topic, as crazy as this is, and I'm being facetious with some of this, but I really like to let it be known that this can be applied to other things. The population of high school teachers has a mean number of years served of 12 and standard deviation of 4. So we sampled 36 teachers, my gosh. And what's the probability that the sample of 36 will have a year served of 11 or fewer? And as you can see, it's a rather low probability. Now, again, 11 is close to 12. Isn't it? Yeah. I mean, 11 and 12 seem like neighbors, but the probability that they'll have a mean among those 36 teachers of 11 or less is rather low. And now, where did that come from? Well, first I calculate the standard error of 4, which came from above, and the square root of 36 for roughly 2/3, 0.67. And then I calculate my z-score, 11 minus 12, divided by 0.67. I just sort of rounded up and called it -1.5. This is the same as the blue whales problem. And we're talking about a value that's below the mean. And of course, the black and the blue curve have a mean of 12. And then I'm going to the left of that. I'm going less than. So we know it's a tail value. And sure enough, I got a z-score of 1.5, negative 1.5. And that tail value is 0.668. But again, this would vex the casual observer. They would come in and say, now, wait a minute, 11 is close to 12. Why would the probability be so low of less than 7%? Well, again, we're talking about a mean of 36 teachers. And when you got that many contributors to the mean, it's unlikely that the mean will be deviant, that will get very different from the population mean. Now, what if I did the other approach? What if I said a population of high school teachers has a mean number of years served of 12 and a standard deviation of 4? But this time, and excuse me, the thing didn't wrap very well. Thanks for waiting. This time, we sample only 2 teachers, which of course is a very low sample size, about as low as it can get besides 1. Now, one thing I intended to do here is broaden the distribution of sample means to really tell the story. Here's for 36, where it was rather tall and skinny, as we would expect, and here's for 2, where it's broad. Okay, so what's the probability that the sample of 2 will have years served of 11 or fewer? And you can see it's a lot higher there. It's 0.36, which is much, much higher than 0.668. And here's where I got all my math. So I said, well, here's the standard error of 4 over radical 2, which is 2.84. And then there's my z-score of only -0.35. And so I would want to get the tail value for -0.35, and sure enough, that's 3.632. What's the difference? The the distribution of sample means was a lot broader. The standard error, which is the standard deviation of the distribution of sample means, was a lot larger, and therefore the z-score was a lot less extreme. And of course, that z-score is going to be much more extreme when I have a large sample size. So let me bring up this extremity of the z-score. You know, the silly one was, going way back, was the MCAT. This z-score here, when I had a sample of only 9, was not terribly extreme, because the distribution of sample means was made up of means from only 9 contributors. But when I involve myself with means from 256 contributors, of course, the z-score is much more extreme. It's much further to the right. So as sample size gets bigger, the standard error gets smaller. The distribution of sample means gets skinnier as sample size gets bigger, and z-scores get larger. So there's a trade-off there. As sample sizes get larger, the distribution of sample means gets skinnier. The standard error gets smaller, but the z-score gets larger. And you can sort of walk through the math on that. When we come back, I want to give just a sort of a nutty example that has to do with body temperature. And body temperature, we're going to assume, is very, very narrowly distributed, which does have an effect on these sorts of problems.